So as we start setting up this to run, we're going to start with the grid menu. A good one to look at first is just get info, which down here in the log window prints out some information. This model has 374,000 cells. And I'll just point out that this model was built specifically to have a fairly low cell count to make it a little more easy to work with during this tutorial. If we were building this to actually do a study on it, we would recommend a higher mesh resolution, but having a low resolution helps us to look at it quickly here. Next thing you can look at in the grid menu, there's a check grid. That's good to do. That does a little calculation on the mesh. It will tell you if there's problems with the mesh. It will give you some statistics on how skewed the cells are and what it's going to do with those skewed cells. For this case, we have a pretty regular mesh, and the grid is in good shape. One thing, when we were looking at the grid info, it's good to look at the extents of the model, see if that is what you thought it would be. And if we look here, we have our extents in meters, as this room being 345 meters across, 144 meters high, which is pretty large for a room, probably not what we intended it to be. And that is because this model was built and the mesh was exported in inches. And that information is not carried through in the mesh files. That's something that we need to set first. So go back to the grid menu again, and we're going to say scale. And to scale from inches, if you're not familiar with inches, is 0.0254 is the factor we want to input to go from inches to meters. So after you've entered 0.0254, say OK. The mesh will be scaled and the view is regenerated. And now if we go to get info, our extents is a more reasonable set of numbers for the size we would think that a room should be. So now that we've done a few settings, let's just save this file again. So we'll go to File and Save. We scaled the mesh, so all the mesh coordinates are different, so it's writing out the mesh again and the settings. So now setting up this model, we'll go we finish the grid menu. We don't need to do any translation. We'll look at the database menu and set up some of the finer points of how this model is going to run. We're going to start with the equations panel and open that up. First, it's got a fairly small list of things that we can set. We're not going to have laminar flow, so we're going to change that to the standard K epsilon turbulence model. We're wanting to track the temperature through the model, so we need to have the energy equation turned on. So I'm going to turn that on. The last item is the mixture model, and the last model we looked at, we were tracking what the mixture was. If you hit that, it opens up more of the window. We can select, it has one mixture set by default. You can add an arbitrary number of mixtures. You can give them all different names. Those mixtures can each have their own properties, so lighter or more dense or however that needs to be. For this model, we don't really need to look at any mixtures, so I'm going to leave that unchecked. So if you just check that now, just uncheck it again. Standard K epsilon, energy on, mixture off is what we're looking for, and then say OK. So the next item under the database menu, we did equations. Now we're going to go to fluid materials. This brings up how the material is defined that we're going to be modeling. By default, it brings up constant density air. And if you have, for a lot of models, all you would need to do, say, is adjust the density and viscosity. If you have a different temperature or pressure, going on, and then you could run it with a constant density. For this particular model, since we're wanting to see how the temperature will affect the movement of the air, there's probably going to be some buoyancy effects in this model. I want to have a variable density. So you click on constant, and I want to change that to inverse with temperature. And what the inverse with temperature condition gives you is a variable density based on temperature. It's not a compressible model that varies with pressure, but the density varies with temperature. The number that you have here is basically you take that number and divide by the temperature in Kelvin, and that will give you your density. So this model is applicable for quite a few different types when you have some kind of variable temperature. For the fluid, we can also set the viscosity and specific heat and thermal conductivity. Very often, if you have a wide range of temperatures in the, say, hundreds or thousands of degrees, you would really want to say, change the viscosity to a Sutherland model and maybe change the specific heat to be a polynomial varying with temperature. For this model, we're going to have some temperature variations, but those variations will not be very large. So we're just going to leave the viscosity and specific heat and thermal conductivity to be the constant values that they are by default. All that we're really changing is the density. So once that is all set, we hit OK, and our fluid properties are set. Looking back at the database menu, going through the items, there is an item for solid materials in case you had, say, a heat transfer through a material, either internally or on a boundary, you can have a solid material. We're not going to worry about that today, so we're not going to set any solid materials. Next item is boundary conditions, and those are grouped into external and internal surfaces and for volumes. So we're going to start with exterior surfaces. So go ahead and select that. That brings us up a box that lists all of our exterior surfaces, and we want to set some of those. So just I'll take you through some of these and how we're going to do that. First, I want to specify how the flow is coming into this room through the vents. We have these light blue vents where flow is coming in. So you want to select inlet vents and then just push the edit button. That brings us up another window to specifically set inlet vents. And again, it is divided into different sections of what is being modeled. Momentum, turbulence, and energy are enabled for us to set. For momentum, we want to set the velocity coming in, and there's different ways to do that. The default way is to specify 3 components in X, Y, and Z direction of the velocity. For this one, we're going to say that we already know what the total mass flow coming in is, and we want to use that. So I want to change from components to specified mass flow in that little pop-up box. And that just gives us one number that we can input. And I'm going to say I already know what this is. It's going to be, we're going to use 6.6 as a value per kilogram in kilograms per second of the total mass flow that's coming into this model. And what Azore is going to do is take that 6.6 kilograms per second, and depending on what the temperature is, it's going to determine a velocity, and it's going to set a uniform velocity coming in the normal direction from that boundary. So for this case, we have that boundary split up into 9 pieces. They all happen to have the same area, so each one of those is going to get the same amount of mass flow coming in. In addition to specifying what is the incoming mass flow and from that the velocity, you need to set turbulence and energy parameters. So I'm going to click on the turbulence tab, and gives me, there's a little pop-up box that gives different ways to specify the turbulence. We're using a K epsilon model. If you knew what K and epsilon are, you could just specify those directly. Often we do not know what those are. So What we're going to use is intensity and hydraulic diameter. And this lets us specify a turbulence intensity and plus say the diameter, a rough diameter of what is the ductor or wherever this flow is coming from. So it's set to 0.05, so 5% intensity in the turbulence, which is a typically used number, somewhere between 1 and 10. And so 5 is right in the middle. If you don't know anything about the turbulence, 5% is a fairly safe number. For the hydraulic diameter, I want that to be the smaller dimension of whatever my flow is coming from. For these small inlets, my small size is about 0.3 meters. So I'm going to change that from 1 to 0.3 meters. And finally, we want to set under energy, we want to set what the temperature is. And I'm going to go ahead and set that to 290. That's about 17 Celsius, 62 Fahrenheit. So we're having cool air come out of these vents. Once these momentum, turbulence, and energy are all set, say OK, and those inlet vents are all set. For our return vents, let me just say, this is under the category of a flow boundary condition, which is one where we specify what the flow is going to be. It's usually used as an inlet. You can also use that as an outlet if you want to specify an outward velocity. A pressure boundary condition is what it says. It's specifying what the pressure is and not the flow rate. That is often used as a outlet condition. You have to have at least one pressure boundary or your model will not be stable. The pressure will not have anything to go to. So for this case, our outlet vents, or the vents say returning to the air conditioning system, are defined here as outlet vents as pressure. We'll just have a look at that. Again, you can specify momentum, turbulence, and energy. The thing with a pressure boundary is you want to define what is happening if the velocity is going backwards. In other words, if there's velocity going into the domain. And it could be that you mean for that to happen. Very often, there'll be some part of a pressure boundary that will have inflow in it, especially when the flow is not yet converged. And so you want it to be set up for that to be stable. Generally, having a zero pressure is what you want and backflow normal to the surface. But if you know something about the turbulence and energy quantities going back, say if you knew what the temperature was going to be going backwards into the domain, you would want to set that temperature here. For our particular case, that's probably a temperature close to what we'll be dealing with, and we don't really expect there to be backward flow, so we're just going to leave that at the defaults. So you don't really need to change anything in that window. Now, we have flow set up to go in and out of our domain, but we want these boxes that are internal. I'll go ahead and close that boundary conditions window so we can talk about this a little more. We want these boxes to have flow going through them. So we want to say that we know that there's fans in these boxes that are drawing flow into one side and that's heating up and going out the other side. So let me just highlight for those, just turn those on in the faces. If you look at the list of exterior faces that are walls right now, we have racks intake, which is the face on one side of those boxes. And then we have racks exhaust, which is the face on other side of those boxes. So we want to change those from being walls to having some kind of flow condition going through them. Before I set that, let me just point out, in order to get back to the display I had just a minute ago, there's these two buttons at the bottom of the screen, which are left and right arrows. These are undo and redo of the display. So to get back where I was, I'll just hit the undo button a few times, and my display is restored to where it was, which is what I'm wanting to keep looking at. So to set those external boundary conditions, change them from walls, I'm going to go back to the database, boundary conditions, exterior surfaces. I'm going to open that back up where we just were. And we have racks intake and racks exhaust listed under walls. So to change that, I just click on racks intake, and at the bottom it has the pop-up of what it is. And just by changing that to flow, it changes that to a flow boundary condition. And it pops up the box of how do you want to set that flow boundary condition. Now we're going to say that we know that the flow going through these boxes is a given velocity. So I'm just going to change that to normal velocity. And again, this is the side that's going into my boxes, but from a modeling standpoint, it's going to be going out of the domain. And to do that with the velocity condition, I just set that to a negative number. So I'm going to set that to negative 0.2 meters per second. So that we know that the average velocity through these boxes, 0.2 meters per second. I'm going to use that. Since this boundary I know is going to be a outlet condition, I'm not going to worry for right now about the turbulence or energy quantities. So we just set the inlet to these racks. I want to change racks exhaust for air going out the other side. I'm also going to change that to a flow. I'm going to change change from components to normal velocity. And we're going to use that same number, 0.2 meters per second. But for this case, we're going to use a positive number since the flow is going to be going out. So on one side we had a negative, this side a positive. So this will have flow going through our virtual boxes. I want to set my turbulence quantities. For this one, I'm going to use, again, intensity and hydraulic diameter. And I'm going to say this flow is coming out from fans that have some kind of grid on it. So there's small openings. So I'm going to change that to 0.01 meters. So 1 centimeter openings that's coming out the back of this box. Under the energy side, I'm going to change that to 325. It's the number I've got here. And that is going to give me some fairly hot air coming out the back. It's about 52 Celsius, 125 Fahrenheit. And we'll hit OK on that. Now those two boundary conditions are listed under flow. We had the question about heat through a wall. And so if I just click on a wall and say edit, you have a number of settings for a wall. Under momentum, you can make it so your wall is moving. If you click on energy, you can see a number of different conditions for that. And what the default is that we have zero heat generation and we have a specified flux of 0. So basically a fully insulated wall. You can set this heat flux to be a certain number, or you can set it to be a specified temperature. You can set it to be a specified temperature that has a thickness with a certain material, so that there is some a coupled boundary condition with, so you don't actually have to put a solid on your boundary. You can have an insulated wall. So there's a variety of things you can do on your wall for heat transfer. All right, so now we've set up all our boundary conditions. Let me close that window. Over on the left, we see our boundary conditions we've moved are now under flow. I didn't quite update my colors. I'll just hit surfaces and back to by type. And now it is figured out that those two boundary conditions are now flow boundaries, and it's colored them light blue. I'm going to go ahead and say, save this database, save those changes I just made. A couple more things to do before we run this. I'm going to go back to the database menu, and we don't really have any more boundary conditions we need to set. The next item is gravity. And since this is going to have some buoyancy effects, we want to make sure we have gravity turned on. Gravity is specified by giving it the downward acceleration. So in the Y component, which we have Y is up, so I'm going to say negative 9.81 meters per second squared going downward. The reference density is probably going to be fairly close to what we're already using. So I'm just going to leave that as is and say OK in my gravity. Now, back to the database menu. A couple more things to set. If you look at solution controls, that brings up a menu that shows how all of the different items that are going to be solved, how they will be solved, what are the constants that are used in convergence. We want to change energy, but it doesn't show up here at first, but if you hit the right arrow to the list, you get some energy, or you can make the window a little bigger, see the energy tab. The energy relaxation is set up if we have more of a momentum driven flow. In this particular case, we're going to have some temperature driving the flow, and in order to make it converge a little faster, I would change 0.95 to 0.98 just to help the convergence go a little faster under the temperature relaxation. After you've done that, go ahead and hit OK. One last thing I want to set before we run the model is the units for temperature. So if you go to Display menu now, and you look at Display Units, that brings up a dialog that sets all of the units to how they're going to be displayed. And if we click on temperature on that list, you'll see that the default for temperature is Kelvin. It's what's used internally in the model. But let's just change that to C for Celsius. So that will help us in our viewing this model and the results and what it's going to look like. When you're done with that, just say OK. Now that really the model is ready to run, but in order to see how it's going to run, I want to set up some monitors so that as it is iterating, I'll have some feedback on what is going on and how well it's doing. So in the database menu, look at solution monitors, and we're going to set some surface monitors. This brings up a window where we can set our monitors. It initially has 0 monitors set. Let's change that to 2. 2 monitors. And as it does, this window gets a little too crowded. So just make that window bigger. You can see all the information there. This lets you give it a name for each monitor, what surfaces it's acting on, and what variable you want to look at on that surface. Since we're looking at a steady state model, we're just going to leave that on iteration. For the first one, let's say we want to look at what is the temperature coming out of our vents, how is that converging? So I'll hit the surfaces button, brings me up a list of all the surfaces, and that surface we want to look at is return vents. So click on return vents and say OK. Now it says surfaces and the number 1 because we have 1 surface selected in that list. If you click on the pop-up menu, we don't want the total velocity. I want to go down here toward the bottom, mass weighted temperature. Give me the average mass weighted temperature going out of that boundary. And now we'll change the name of that to give it something that makes a little more sense with what we're doing. I'll say T average vents. For the second one, let's say we want to know something about the temperature going into our electronic racks. So I'll hit the surfaces button on that second item. And the inlet to those boxes is the one we just specified as racks intake. So I want to select that. And for this one, just to do something a little different, I will say the maximum temperature at the very bottom of the list is what I want to look at. And I'll just rename that to T max racks. You can name those whatever you like, just so you know what it is later. Once those are both set up, I'm going to say OK. And now we're really ready to run.